So now that we have a bunch of limit laws, let's put together a problem-solving strategy for calculating a limit when f of x over g of x has the indeterminate form 0 over 0. First, we want to check that the function is an intermediate form and cannot be evaluated immediately using limit laws. If we can just use limit laws like we did in the last few examples, then it should be easy, quick, done. But if we can't, then we're going to go through and follow these steps. So then what you're going to do is you're going to find a function h of x that is equal to h of x equals f of x over g of x for all x not including a over some interval containing a. So to do this, we're going to try one of the following steps. So what we did on the last slide is we took f of x and g of x were polynomials and we factored each function and canceled out any common factors. And that got it where we can actually apply the limit laws to evaluate it. You can also see if the numerator or denominator contain a difference involving a square root. If that's the case, try multiplying the numerator and denominator by the conjugate of the expression involving the square root. We're going to do this in a future slide. If f of x over g of x is a complex fraction, so complex fraction, recall, is when you have a fraction within a fraction, simplify it first. And then, hopefully at this point, you'll be able to finally apply limit laws. So let's look at this example. Use limit laws to evaluate the limit as x approaches 0 of the square root of x squared plus 9 minus 3 all over x squared. So at this point, when I look at this problem, I see that if I substitute 0 in for x, I'm going to get 0 in the numerator and I'm going to get 0 in the denominator. So I'm in that indeterminate form 0 over 0. So I've done step 1 where I've realized, shoot, I'm in this form. So now let's do step 2. So step 2 said we need to find a function that's equal to this and do one of the following steps. So if they're polynomials, factor functions out. So we can see that numerator is not a polynomial because we have a square root in it. Letter B for step 2 said if the numerator or denominator contains a difference involving a square root, we should try to multiply the numerator and denominator by the conjugate of that expression. Okay, so let's do that. Because I do have in the numerator, I do have a square root and we're doing the difference. So the limit as x approaches 0 of the square root of x squared plus 9 minus 3 all over x squared. All right, so to be able to simplify this or to kind of change around what it looks like, let's go through and take this function. Actually, let's take the square root. Let's just do this kind of on the side. I think it'll be a little bit easier to find this other function. Okay, so let's take this and we're going to multiply both the numerator and the denominator because we need to keep this equation balanced by the conjugate of that square root. So the conjugate is going to be x squared plus 9 plus 3. So instead of subtracting 3, we add 3. That's what the conjugate means. And whatever I do to the numerator, I have to do to the denominator to keep that fraction balanced. Now, I like to call this a fancy one or math magic. Okay, so when we do this, that's going to end up giving us, when I multiply those two together, it's going to undo that square root. So we're just left with x squared plus 9. Here I'm going to get plus 3 times the square root of x squared plus 9 minus 3 times the square root of x squared plus 9 minus 9 all over x squared times, I'm not going to factor this guy out yet, the square root of x squared plus 9 plus 3. All right, so now that I have this, the reason we multiplied by that conjugate is because in this case, it gets rid of that square root in that numerator. So we're going to be left with, so those are going to cancel out, and then also we've got a plus 9 and a minus 9. So we're going to be left with x squared over x squared times the quantity square root of x squared plus 9 plus 3. Now we can also see we can cancel out those terms, which is going to leave us with 1 over the square root of x squared plus 9 plus 3. So what I did is I took this function and I changed it into a different function. They're still equal, But now this is something that I can evaluate. So the limit as x approaches 0 of this, I can put this in for it. Square root of x squared plus 9 plus 3. Now I can actually go through and substitute in that 0. This is going to allow me to do that. So we'll go through and we'll do some limit laws on this. So it can take the limit as x approaches 0 of 1 in the numerator over the limit as x approaches 0 of the square root of x squared plus 9 plus the limit as x approaches 0 of 3. So the limit as x approaches 0 of 1 is just 1. Down here, I can move that limit inside of the square root. So take the square root to the outside using those limit laws. So I get that. Plus the limit as x approaches 0 of a constant is just the constant, so plus 3. So now looking here, what we're taking the limit of is x squared plus 9, which is just a polynomial. So I can actually just now go through and substitute in 0 for x. So I'm going to get 0 squared plus 9, which is 9. So that leaves me with 1 over 3 plus 3, which is 1 over 6. So you can see here what we did is we took something that was in that indeterminate form 0 over 0 where I could not substitute in x equals 0. And I took this function and I used a little bit of math magic to multiply by a fancy one, which was the conjugate. So again, the conjugate is you change up, you do the opposite sign. By doing that, that's what left me with these two terms being able to be canceled out. So it got rid of that square root in the numerator so that then I was able to get it to a point where I could actually evaluate the limit as x approached 0. All right, let's continue looking at examples. So use the limit laws to evaluate the limit as x approaches 1 of 1 over the quantity x plus 1 minus 1/2 all over x minus 1. So in this situation, I have what's called a complex fraction because I have a fraction within a fraction. Let's see if we can first just substitute 1 in for x and get a value. So when I do that in the numerator, I get 1/2 minus 1/2, which is 0. And then in the denominator, I get 1 minus 1, which is 0. Shoot, this means I'm in that indeterminate form. So let's use those problem-solving strategies to go through and solve this. All right, so step 1 in the problem-solving strategy was to check if you were in indeterminate form, which we are. So step 2 was to find another way to go through and use this expression, write this expression into a way that we can actually evaluate it. So when we have a complex fraction, we need to simplify this. So what I mean by simplifying, you might need to go back to what we did in intermediate algebra when we dealt with complex fractions, is we need to get it so we don't have these fractions within fractions. There's two different methods for doing that. The method that I usually use is what I'm going to show. So the method that I typically use is you multiply both the numerator and the denominator by the common denominator of the fractions. So we can see here I've got x plus 1 and 2 are my fractions within the fractions. So the common denominator, if I were to combine these two, is going to be 2 times x plus 1. So I can't just multiply the numerator by that, I have to also multiply the denominator by that so that this equation is going to stay balanced. Okay, so again, this is my fancy one using some math magic to change how this function looks. All right, so to find an equivalent one that we can actually evaluate. So what we need to do now is distribute this to each of those terms. So when I do that, I'm going to get 1 over x plus 1 times 2 times x plus 1 minus 1/2 times 2 times x plus 1. And then that's all over x times, I'm going to actually just, to make life a little bit easier, we'll do this. Well, we can keep it the same. So 2 times x plus 1 minus 1 times 2 times x plus 1. So all I'm doing is just showing that each of these terms has to get multiplied by that to keep this equation balanced. So what's great about that is that these denominators will cancel out and it's going to help us simplify these. So when I do that, I'm going to be left with the limit as x approaches 1. In the numerator, I'm going to have 2 is what that first term becomes. The second term becomes minus that quantity x plus 1. Remember, we're subtracting this whole thing. And then that's going to be all over, let's see, we're going to get 2x squared plus 2x minus 2x minus 2. All right, so that is going to end up giving us the limit as x approaches 1 of 2 minus x minus 1 all over 2x squared minus 2. So the limit as x approaches 1 of negative x plus 1 all over 2x squared minus 2. So at this point we can say, okay, can I actually evaluate this? So it's a lot simpler than what we started with. So at this point is where I'm going to check if I can do that. So if I substitute 1 into the numerator, I get 0. If I substitute 1 into the denominator, I also get 0. So we're not done yet. All right, now we got to go back to that drawing board. So let's go back to that problem solving strategy and look back at step 2 again. So now I don't have a complex fraction, but I do have a polynomial or a rational function. So let's see if I can factor anything out and cancel any terms. All right, so I'm going to show you a fancy factoring thing. But before I do that, I'll factor the bottom so you can see why I'm going to do the fancy factoring. So this is going to factor into 2 times x squared minus 1, which gives us negative x plus 1 over 2 times x plus 1 times x minus 1. So right now looking at this, I see that, shoot, it doesn't look like anything is going to factor. However, these are eerily similar, except they're flipped. So what I can do, this is just a factoring trick, is I can factor a negative 1 out of that numerator. If I factor a negative 1 out, negative x divided by negative 1 is positive x. Positive 1 divided by negative 1 is negative 1. So you can see if I distributed this negative through, I'd get negative x plus 1, which is this. So these are equivalent. But the reason that I'm doing that, hopefully you can see by now, but if you can't, I'm going to show you, is that by doing that way, now I can see this term, which is causing me all the problems, because when I substitute 1 in for x there, I get 0, is going to be gone. And I'm left with the limit as x approaches 1 of negative 1 all over 2 times x plus 1. Now I'm not in indeterminate form anymore. Now I can actually evaluate this limit. So this is a rational function. We have a polynomial divided by a polynomial. So all I have to do is, and let me just check to make sure that denominator will not equal 0. So when I substitute 1 in for x, I get 2 times 2, which is 4, so that works. So all I have to do now is just anywhere I see an x, substitute in a 1, and I get negative 1 over 2 times 2, which is negative 1/4. Phew. So that took a lot of steps, but it made it where we had this function that we couldn't actually evaluate into one that we could. Okay, and the last piece that we're going to learn about in this section is evaluating a limit using the squeeze theorem. Now in my class, we're not going to actually have you guys apply this, but it is something you need to be exposed to and you need to know is out there. So for example, if we have something like this, evaluate the limit as x approaches 0 of x times the cosine of 1 over x. Right now, if I substitute 0 in, I'm going to get 0 times the cosine of 1 over 0, which is indeterminate form. So I run into an issue where I can't actually evaluate that limit. And this is where the squeeze theorem comes into play. So I can't use that problem solving strategy that we had before because I don't have something that's 0 divided by 0. So the squeeze theorem, here's what it says. It says, let f of x, g of x, and h of x be defined for all x that are not a over an open interval containing a. If I can find, so if this is our original function we're starting with, if I can find a function that is smaller than it and greater than it for all x that are a, then I can figure out if the limit of this smaller function and the limit of the larger function equal that same value. I can then conclude by squeezing that together that the limit of this has to also be that same value. So let's think about this. So remember with the cosine graph back in trigonometry, that cosine graph, the maximum value that that cosine graph takes on is 1. The minimum value it takes on is -1. So I know that this is going to be greater than or equal to -1 or less than or equal to +1. So if I'm looking for that f of x and h of x, here's what I would do. So I can find a function that's going to be less than or equal to that would be -1 times x, because I can replace that cosine with -1 since that's the smallest that can ever be. The largest that can ever be is 1, so 1 times x is x. So I can say that this function has to be between -x and x as x is approaching 0. Now the reason I'm doing that is, check this out. These are easy functions for me to evaluate. The limit as x approaches 0 of -x, well, this is just a polynomial, so I can just substitute that 0 in and I get -0, which is 0. All right, let's look at this second function. The limit as x approaches 0 of x, again, polynomial, so I can just substitute that in, is 0. So the limit of -x as x approaches 0 is 0. The limit of +x as x approaches 0 is 0. So we can then conclude that the limit of this in between function is 0.